Have you ever just stopped and wondered if there's some kind of hidden language, like a single set of rules that could describe and, maybe even control almost any complex system you can think of? Well, today we're going to dive into a theory that tries to do exactly that. And it all starts with a question that sounds pretty simple on the surface. I mean, it sounds like the start of a strange joke, right? You've got biology, sophisticated engineering, and this huge, sprawling social structure. They seem like they're from completely different universes. But what if they aren't? What if deep down they share some kind of fundamental blueprint? That's the core question this really fascinating field, Axiomatic Systems Theory, or AST, is trying to answer. Look, scientists and engineers are always wrestling with how to get a handle on these incredibly different systems, and AST comes along and offers this kind of revolutionary idea, a universal framework. It's basically a search for the fundamental grammar that all complex systems follow, built from the ground up on what we call first principles. Just think about it for a second. The software running on your phone, the crazy dance between a virus and your immune system, they all seem to have their own unique, super complicated rulebooks. But what AST suggests is that if we could just peel back all the layers, underneath all the surface details, we'd find a common structure, a shared set of rules that actually connects all of them. Now, this whole idea of starting from the absolute basics, it's not new at all. The axiomatic method is actually ancient, and it's an incredibly powerful way to think. It's all about starting with a handful of simple, undeniable truths, and then building an entire logical world on top of them. So check this out. On the left, you've got Euclid's geometry. This is the classic example. The guy starts with a few basic truths, we call them axioms, like you can draw a straight line between any 2 points. Simple, right? But from just a few of those, he built the entire field of geometry. So the big question AST asks is, on the right, can we do that for everything else? Can we find the basic axioms for biology, or for software, or for an economy? And here's the crucial thing. The axiomatic method isn't just some dusty old philosophical idea anymore. It's evolved. Today, it's a really powerful, practical tool. It's used in fields like computer science to build what's called verifiable software, basically code that we can mathematically prove is correct, all because it's built on a solid foundation of rules. Okay, so if that's the tool, how does it actually define a system in a way that works for everything? Well, it turns out the answer is just shockingly simple and elegant. So here it is, the core of the whole thing. Any system, and I mean any system, can be boiled down to a pair of things, S and C. S is just the stuff, the set of parts. Think of it like a big pile of Lego bricks. But a pile of bricks isn't a spaceship, right? For that, you need C. C is the structure of rules, the instruction manual that tells you exactly how all those bricks connect and interact with each other. And that's it. Parts and rules. From a living cell to an entire society, it's all just parts and rules. Okay, so you've got your parts and you've got your rules. What's next? Well, how do you influence the system? How do you control it? This is where the theory gets really deep, connecting the idea of control to something super fundamental, the simple act of choice. Think about it like this. To control anything, you have to be able to pick one action from a whole menu of possibilities. At a really deep mathematical level, the principle that guarantees you can always make a selection is something called the axiom of choice. So by linking the practical idea of control to this core mathematical idea of choice, AST can talk about controlling systems in a totally universal way. All right, I know what you're thinking. This all sounds very abstract, very theoretical. But what does it actually do? Why should we care? Well, this is where it all comes together and becomes an incredibly powerful tool. It gives us a common language for different fields that are trying to talk to each other, like the world of pure software and the messy physical world it's trying to control. This quote really just nails the sheer ambition of this whole thing. It's not just about building better robots or software. It's about finding a framework, a language, that's powerful enough to describe the fundamental patterns that govern reality itself. It's a huge idea. And this, right here, is where a theory like AST really starts to shine. Because let's be honest, a lot of real-world systems are just too messy, too chaotic, or too poorly understood to fit into a nice, neat set of equations. When our usual math tools just can't get the job done, we need a different way of thinking. We have to go back to those first principles. So let's actually look at how this works out in the real world. This axiomatic approach gives us a way to build models of systems even when we don't have all the pieces of the puzzle, letting us tackle some ridiculously difficult problems.
Okay, this table lays out a few awesome examples. First up, symbolic models. This is how you build a bridge between the digital world of software and the physical world of hardware. You create an abstract model that both of them can understand. Then you've got axiomatic design, or AD. This uses axioms to judge if an engineering design is actually any good, which is a lifesaver when you're comparing really complex plans and you don't have all the data yet. And my favorite, in biology, we can model the crazy battle between a virus and our immune system not by trying to write one single perfect equation, but by building a model that just has to follow a basic set of rules, axioms, about how they both behave.
And that really brings us to the ultimate prize here. Axiomatic systems theory isn't about finding some magic formula that explains everything. It's about finding the fundamental logical rules, the first principles that any good model of any system has to follow, whether that system is a machine, a living thing, or a society. It's about building a solid foundation for understanding complexity itself. So, I'll just leave you with this thought to chew on. If we could really do it, if we could create this perfect universal language for describing systems, this grammar for reality, what's the first problem you'd want to solve? Would you take a crack at climate change, curing a disease, maybe designing a truly stable economy? The possibilities are literally as endless as the systems all around us. Maybe, just maybe, the biggest problems out there aren't waiting for a new discovery, but just for a better language.